Hello, my name is Šimon Tóth and thank you very much for choosing my talk. Now, this talk will be on my favorite topic, which is the different issues you can run into when using C++. And specifically in this talk we will talk about the MinMax algorithms from the standard template library. Before I start with the talk proper, a little bit of bookkeeping. This is a permanent link for the slides. You can get the PDF to follow along. You will find links to all the code samples and all the references that I talk about in this talk. Now, because this talk is pre-recorded, there is a second me right now answering questions as the talk is going on. But if you want to ask questions for later, please do take note of the slide number so I make sure that I know what you are talking about and what your question is actually about. Second, I want to point you to another talk about MinMax algorithms, which is from Walter Brown. That talk is specifically about the algorithmic side of things, that is how you would actually go about correctly implementing a MinMax algorithm, also about the nuances of the less than comparison, especially for floating point numbers. Now, this talk is perfectly complementary to my talk, so if you are interested in actually implementing MinMax algorithms, I definitely recommend that you go and watch it. There are multiple recordings on YouTube already. My talk actually started when I was working on my book, on my free book, and when I was working on it, I tried to think about the different difficulties that you can run into when you are working with the standard algorithms. And well, there are plenty of small things for sure. Some of the algorithms have misleading names. Some of the algorithms have relatively complicated rules about how the input and output ranges can overlap. And of course, many of the algorithms can be customized using a functor. And often the rules for what exactly the functor is allowed to do can be also quite complicated. Well, after thinking for a while about this, I actually realized that really it's the MinMax algorithms that are the most difficult part of the standard algorithms. And that's why today I would like to explore with you the question, how hard is it to actually call standard min? Well, at this point, you might be slightly confused. And that would be understandable because, well, I mean, calling standard min is pretty easy, right? And yes, there is nothing wrong with this line of code. It's perfectly all right. We can also call standard max in the same way. Again, there is nothing wrong. We can also call clamp, and I'm kind of putting clamp into the category of MinMax algorithms because it is kind of MinMaxy. If you are not familiar with this algorithm, it takes 3 arguments. The first argument is the value, then the lower bound and the upper bound. If the value is between the bounds, then the algorithm returns the value. If the value isn't between the bounds, then it returns one of the bound. And as I said, again, even for clamp, there is no issue. But we very quickly run into a big problem if we try to call MinMax in the same fashion. And well, the trouble that we run into is actually dangling references. To understand why this is actually happening, we have to look at the function prototypes for these algorithms. And you might already notice the difference. First of all these functions take their arguments by const reference. And most of them just simply return by const reference as well. The difference is, of course, MinMax. MinMax returns a pair of const references instead. And to understand why this is an issue, we can kind of rewrite the line using the auto to be a little bit more explicit. This is actually the equivalent line from the 2 slides back. We call MinMax, and we store the result into a pair of const references. Now, the reason why this ends up with dangling references is very simple. The lifetime rules in C++ say that if you have temporaries inside of an expression, these temporaries will be alive for that expression. However, the moment the expression is finished evaluating, those temporaries are destroyed. And what we have here is we are storing two const references that are pointing to temporaries, in this case the literals 1 and 2. We can actually trigger the same kind of issue even for standard min. In this case, we have to explicitly capture by const reference. Now, you might be wondering, well, okay, where is the difference then? On the 2 slides back, we are capturing by auto, and why does this work for min and not for MinMax? Well, the tricky part is that if we are capturing by auto, auto follows the template type deduction rules, which means that auto will never deduce a reference. So in this case, auto will deduce an int. And because we are capturing by value, what we are making is a copy. We will copy the result, which at that point is still perfectly alive. It is one of these temporaries. And once we have copied the result, well, then we are past the expression, but we have a copy. We don't care about the lifetime of those temporaries anymore. Now, why this doesn't work for MinMax is because what we are capturing by copy here is the pair itself, not the const references inside of the pair. So the auto doesn't really save us here. You might be wondering whether we could use structured bindings, for example. Unfortunately, structured bindings don't allow any sort of flattening of types. We can control how we capture the outside type, in this case the pair. We can still capture it by reference or by copy. But the names of the types of the x and y will match the types inside of the pair. The only case where this wouldn't happen is if you would further CV qualify the capture of the type of the outside type. Now we can save the call by explicitly storing the value in a pair of ints. In that case, what happens is that as part of the expression, we are again making a copy. And in this case, a copy from a pair of 2 const int references into a pair of ints. Now, the really sad part here is that, unfortunately, there is no way to detect this at compile time. None of the compilers that I have tried will issue a warning. And the same goes for static analyzers. I tried clang tidy and CppCheck. And the only way I was able to trigger some sort of error on this particular issue is if you use address sanitizer, and then at least you get the line numbers if you have debug information. However, remember that address sanitizer is a runtime check. So this means that you actually need to exercise this code to see the error. Well, all right, so we have a bit of an issue with MinMax specifically, and if we are not careful with some of the other MinMax algorithms. But some of the different versions of C++ introduce variants of these algorithms, so let's have a look. Maybe some of those are better. Well, I will start from the newest, which is C++20. And unfortunately, the range versions of these algorithms behave exactly the same. Now, we did get one more overload, which takes a range and returns by value. However, this overload isn't really interesting for the context of this talk. From my perspective, really, this overload you would only use if you have a temporary range and you want to calculate min-max on top of this range. So if you are in that situation, this might be the overload for you. However, we have a little bit more interesting variants that were introduced in C++14. These variants take an initializer list and return by value. So sounds promising. So let's have a look. And yes, indeed, if we use these variants, we get rid of the issue completely. And it's simply because these functions return by value. Now the deduced type will be int or pair of ints, and we don't have any dangling references anymore. So, sounds good. And we can even go further, and if we accidentally capture by const reference, we also don't get an issue, because now we are actually hitting the lifetime extension rule. Now, this rule is simply that if you have a temporary and you bind it to a reference, well, then the lifetime of the temporary is extended to the lifetime of the variable. So here, the temporary that's being returned from standard min will be extended to the lifetime of the variable z. Now, sadly, these variants of min and max have the same issue that the initializer list has, because they are using initializer list. Now, initializer list is a very simple type. It's effectively a wrapper around the const array. Sadly, that means that this const array needs to be initialized, and it's initialized by copy initialization very explicitly. And because it is const, well, then you cannot move out of it. This fundamentally means that you cannot use these overloads for move-only types. Well, okay, that's a little bit exotic, so let's look a bit further. It also unfortunately means that if you have types that are expensive to copy, well, then you will be paying a lot for the copies. Because if we simply call standard min using an initializer list, we occur 3 copies. The 2 copies are the initialization from A and B, and then the third copy is the actual return. Now, fortunately, if we have temporaries, the situation is actually much better, because this hits one of the very explicit copy elision rules from C++17, where if we are copy initializing from PR values, that is temporaries, that copy initialization will turn into a direct initialization. So here we don't incur any copies. Well, we incur 1 copy, and that 1 copy is for the one of the 2 returned arguments. All right. So technically right now, we have 2 sort of buckets of MinMax algorithms. We have the original that take by const reference, and those are great for L values. And we have the initializer list variants, and those are great for temporaries, PR values. Unfortunately, I still need to mention one more issue, which is issue with const correctness. Well, you see, the problem is we could have code like this. And what we are actually doing here very fundamentally is we are figuring out which of these 2 variables is the minimum, and then calling a method on that. Now, that's kind of cumbersome, so it would be very nice if we could do this. And we technically can. The only limitation really is that do something needs to be a const method. Well, why? It needs to be a const method because standard minimum returns const reference. So that means only const methods can be invoked. Well, but we are passing in 2 mutable references. That is A and B, those are mutable variables. So can we somehow get back to a mutable reference? And we can use constcast. Now with constcast, the method is totally fine to mutate the state of A and B. However, you might argue that at this point, maybe we should just stick with the if, because this is becoming quite cumbersome. And if we are working with programmers that are not super familiar with C++, constcast isn't a very typical cast. So it might be also quite a surprising code. Well, all right. Let's say we kind of agree that constcast is okay. It still doesn't quite work because this code is also quite brittle. What happens if in the future someone comes in and edits this code, makes the original variables const? Well, now we have a big issue. To be clear, the issue is not with constcast. Constcast is perfectly fine to cast away const as much as it desires. The problem comes in if we try to mutate the state of a variable that was originally declared as const. So as long as do something doesn't actually mutate state, we are fine, but the moment it does, we have a big issue because we have undefined behavior. All right. So that's a lot of issues that I have just talked about in a relatively short time span. So can we fix it? It would be nice to, maybe propose some alternatives, not necessarily to fix the standard because that's a tedious process, but you might want to implement your own MinMax algorithms or something to that effect. So what do we actually want to do? Well, first of all, it would be nice if we didn't have to constcast. If we pass into mutable L values, well, there really isn't any reason to not get an mutable L value back. If we have temporaries in the expression, well, we have seen the solution. The initializer list actually does solve the issue by returning by value. So if we have a temporary in the expression, let's just return by value. And finally, let's get rid of the issues from initializer list, and let's not have any excessive copies. Specifically, really, the only thing we want to copy is the argument that we are returning, and only if we are returning by value. So can we do this? Well, it's always good to start with a simple solution as a baseline. So let's just try a very simple brute force solution, which is just adding more overloads. We can start with the basic overload. And to get rid of the const issue, we don't really have to go too far. The only thing we really need to do is just add another overload that accepts mutable references. And now, if we call this function with two mutable references, we end up with overload 2, returning a mutable reference. If we call this function with one of the arguments being const, we default back into the first overload. So good, we have solved that issue. What about returning by value if we have a temporary as one of the arguments? Well, that's not so nice, unfortunately. The tricky part here is because the two arguments are bound together with the same type, we kind of have to introduce the variance where const can be on either side. If we didn't, well, then we would end up with situations where we would have const R values, which is something we definitely don't want to have. However, just adding these two does cover all the situations, except it does create another issue, which is, well, what happens if we pass in two temporaries, two PR values? Well, in that case, the two overloads 3 and 4 are equally as good. So we need to add a fifth one, and this one will actually finish the overload set. And yes, this is pretty horrible. But it does work. And to be fair, it is just C++11, and there is no complicated logic here except for simple overload selection. So you could technically use this, and again, it does just work. If we pass into mutable references, we get back a mutable reference. If we pass in two temporaries, well, we get return by copy, return by value, and then we can capture it by const reference, it gets life extended, everything is fine. And the same logic can be applied to MinMax as well, in which case it just returns by value, and we get a copy, everything is fine. So, all right, we have a baseline. It works, it's really horribly verbose, it's relatively simple, so can we do better? And here I have to thank Luke for getting me on the right track, because originally my ultimate solution was not that ultimate. So thanks again, Luke, for this very, very neat solution. So what we can do is jump to C++20, which is kind of sad, but you could technically make an intermediate solution that would work with older versions of C++. But what we can do is decouple the two arguments. Now, both of the arguments will deduce their type independently, and because of that, one of them can be const and one of them can be mutable. And because we are simply returning reference, what this means is this simple one overload covers both the const and mutable reference situation. So this covers the overloads 1 and 2 from the previous solution. And then to add support to return by value, if one of the arguments is a PR value, well, all we need to do is simply have another overload. And this is it. Now, this is almost it. You could use this as it is, but it does have few ergonomic issues. So let's just go through that and make it perfect. The first thing I want to mention is not really an issue as such, more is a misleading statement I made on the previous slide. You see, the ternary operator that I used there is actually quite important. If you would rewrite the function with an if, well, then we have a problem because at runtime we could have two different types returned from this function. If you pass in a const reference and a mutable reference, well, then one path can return a const reference, the other path can return a mutable reference. Those are conflicting types. The thing is, the ternary operator actually returns a union of CV qualifiers for the two arguments that you pass in. Meaning that it has this selection logic that if either of the arguments is const, the result is const. So we want to kind of mimic that. And we can mimic that. There is actually utility for specifically this reason in the standard. It's called common reference. Now we have only changed the result type of this function from L-value reference to a common reference between the two arguments. Now that was just a side note. Let's look at the first actual issue. We have actually significantly changed the behavior of this function because now the types are decoupled. This means that, well, we can pass in two completely separate types, and that might not be quite what we want. So what we really want to do is to kind of constrain this function. And yes, for that we would use constraint specification from C++20. So what we can say is that we want the two types to be the same. That is, after we have removed the CV qualifiers and the top-level reference. Now the second issue is actually in the overload that returns by value. Now this issue is slightly more subtle. If we pass in temporaries into this function, they still end up getting copied, which is good because we are copying only the thing that we are returning, but technically what we want is actually a move. But on the other hand, if we pass in an L value with a PR value, we don't want the L value to get moved. So to solve that, we have a tool for that in the standard as well, which is forward. Now forward will correctly forward the type passed in, and it will either move or copy depending on whether the argument is an L value or an R value. All right, so if you put this together, it actually does fit on one slide, so it's not too horrible. It is a bit wordy because we have all these utilities that kind of need the expansion with templates, and it's not superb, but it's quite succinct. Now, so far I just shown you the min, but you could apply exactly the same logic to MinMax. The only difference really is that you need to take a little bit more care because with MinMax, the ternary operator doesn't really do the heavy lifting for us. So you kind of need to go back to the case where we explicitly used an if, and we need to use a common reference to figure out the common reference between the two arguments, and then instantiate the pair we are returning using that reference. And with that, we are done. We have a solution that gets away from the const case, correctly copies when we pass in a temporary, and only copies when it needs to, or also only moves where it needs to. So how hard is it actually to call standard min? Well, it's not that hard, but do be careful, these functions are pretty sharp. Thank you. All right, so we have some questions. So the first question is, do you think Const is acceptable solution given the trade-offs? I really don't like it. It's very brittle. The problem is, on the slide, it looks very easy because it's so close together, right? But in reality, the variables are probably much further away from the Const, so it's quite easy for someone to make the defensive solution, change something to Const, and suddenly you have a big problem. So I wouldn't really use Const unless the variables are very close to the actual call. Okay, second question. Can you post the GitHub for the book in Discord? You took it away before I could grab it. Sure. So it's actually linked from the slides, and the slides should be already linked in the talk, like in the program. So I will also post the link as well.